School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 3 Sampling and Sampling Distributions. Unit 11 Testing of Hypotheses.
After completing this unit, you should be able to understand the meaning of statistical hypothesis, absorb the concept of the null hypothesis, appreciate the importance of the significance level and the p-value of a test, learn the steps involved in conducting a test of hypothesis, and perform tests concerning population mean, population proportion, difference between the population means, and two population proportions. Introduction. In this unit and the next, we shall study a class of problems where the decision made by a decision maker depends primarily on the strength of the evidence thrown up by a random sample drawn from a population. We can elaborate this by an example where the purchase manager of a machine tool making company has to decide whether to buy castings from a new supplier or not. The new supplier claims that his castings have higher hardness than those of the competitors. If the claim is true, then it would be in the interest of the company to switch from the existing suppliers to the new supplier because of the higher hardness, all other conditions being similar. However, if the claim is not true, the purchase manager should continue to buy from the existing suppliers. He needs a tool which allows him to test such a claim. Testing of hypothesis provides such a tool to the decision maker. If the purchase manager were to use this tool, he would ask the new supplier to deliver a small number of castings. The sample of castings will be evaluated, and based on the strength of the evidence produced by the sample, the purchase manager will accept or reject the claim of the new supplier and accordingly make his decision. The claim made by the new supplier is a hypothesis that needs to be tested and a statistical procedure which allows us to perform such a test is called testing of hypothesis. What is a hypothesis? A hypothesis, or more specifically a statistical hypothesis, is some statement about a population parameter or about a population distribution. If the population is large, there is no way of analyzing the population or of testing the hypothesis directly. Instead, the hypothesis is tested on the basis of the outcome of a random sample. Our hypothesis for the situation could be that the mean hardness of casting supplied by the new supplier is less than or equal to 20, where 20 is the mean hardness of castings supplied by existing suppliers. A two-action decision problems. The decision problem faced by the purchase manager in this situation has only two alternative courses of action: either to buy from the new supplier or not to buy from the new supplier. The alternative chosen depends on whether the claim made by the new supplier is accepted or rejected. Now, the claim made by the new supplier can be formulated as a statistical hypothesis, and therefore the decision made or the alternative chosen depends primarily on whether a hypothesis is accepted or rejected. Some basic concepts. We shall now discuss some concepts which will come handy when we attempt to set up a procedure for testing of hypothesis. The null hypothesis. A hypothesis is a statement about a population parameter or about a population distribution. In any testing of hypothesis problem, we are faced with a pair of hypotheses such that one and only one of them is always true. One of this pair is called the null hypothesis and the other one is called the alternative hypothesis. The null hypothesis is referred to as H0 and the alternative hypothesis is represented as H1. It is not difficult to identify the pair of hypotheses relevant in any decision situation. Can any one of the two be called the null hypothesis? The answer is a big no, because the roles of H0 and H1 are not symmetrical. One can conceptualize the whole procedure of testing of hypotheses as trying to answer one basic question. Is the sample evidence strong enough to enable us to reject H0? This means that H0 will be rejected only when there is a strong sample evidence against it. However, if the sample evidence is not strong enough, we shall conclude that we cannot reject H0, and so we accept H0 by default. Thus, H0 is accepted even without any evidence in support of it, whereas it can be rejected only when there is an overwhelming evidence against it. Perhaps the problem faced by the purchase manager in the given situation will help us in understanding the role of the null hypothesis better. The new supplier has claimed that his castings have higher hardness than the competitors. The mean hardness of casting supplied by the existing suppliers is 20, and so the purchase manager can test the claim of the new supplier by setting up the hypothesis test. The null hypothesis is called by this name because in many situations the acceptance of this hypothesis would lead to null action. For example, if our purchase manager accepts the null hypothesis, he would continue to buy castings from the existing suppliers, and so the status quo ante would be maintained. On the other hand, rejecting the null hypothesis would lead to a change in the status quo ante, and purchase is to be made from the new supplier. Type 1 and Type 2 errors. Since we are basing our conclusion on the evidence produced by a sample, and since variations from one sample to another can never be eliminated until the sample is as large as the population itself, it is possible that the conclusion drawn is incorrect, which leads to an error. There can be two types of errors. If the purchase manager rejects H0 and places orders with the new supplier when the mean hardness of the casting supplied by the new supplier is in reality no better than the mean hardness of castings supplied by the existing suppliers, he would be making a type 1 error. In this situation, a type 2 error would mean not to buy castings from the new supplier when his castings are really better. Both these errors are bad and should be reduced to the minimum. However, they can be completely eliminated only when the full population is examined, in which case there would be no practical utility of the testing procedure. On the other hand, for a given sample size, these two errors neutralize each other, as we will learn later in this unit. This implies that if the testing procedure is designed as to reduce the probability of occurrence of type 1 error, simultaneously the probability of type 2 error would go up and vice versa. What can at best be achieved is a reasonable balance between these two errors. In all testing of hypothesis procedures, it is implicitly assumed that type 1 error is much more severe than type 2 error and so needs to be controlled. If we go back to the purchase manager's problem, we shall notice that type 1 error would result in a real financial loss to the company, since the company would have switched from the existing suppliers to the new supplier who is in reality no better. The new castings are no better and perhaps worse than the earlier ones, thus affecting the quality of the final product or machine tools produced. On top of it, the new supplier might be given a higher rate for his castings, as these have been claimed to have higher hardness. And finally, there is a cost associated with any change. Compared to this, type 2 error in this situation would result to an opportunity loss, since the company would forego the opportunity of using better castings. The greater the difference in cost between type 1 and type 2 errors, the stronger would be the evidence needed to be able to reject. H0, that is the probability of type 1 error, would be kept down to lower limits. It is to be noted that type 1 error occurs only when H0 is wrongly rejected. The significance level. In all tests of hypothesis, type 1 error is assumed to be more serious than type 2 error, and so the probability of type 1 error needs to be explicitly controlled. This is done through specifying a significance level at which a test is conducted. The significance level therefore sets a limit to the probability of type 1 error, and test procedures are designed so as to get the lowest probability of type 2 error subjected to the significance level. The probability of type 1 error is usually represented by the symbol alpha, and the probability of type 2 error is represented by the symbol beta. Testing of hypothesis suffers from the limitation that the financial or the economic cost of consequences are not considered explicitly. In practice, the significance level is supposed to be arrived at after considering the cost consequences. It is very difficult to specify the ideal value of A in a specific situation. We can only give a guideline that the higher the difference in cost between type 1 error and type 2 error, the greater is the importance of type 1 error as compared to type 2 error. Consequently, the risk or probability of type 1 error should be lower, that is, the value of A should be lower. Here A means alpha. In practice, more tests are conducted at alpha equals to 0.01, alpha equals to 0.05 or alpha equals to 0.1 by convention as well as by convenience. The power curve of a test. Let us go back to the purchase manager's problem referred to earlier, where we set up our hypothesis. These hypotheses imply that the purchase manager would normally accept the null hypothesis that the mean hardness of castings delivered by the new supplier is not above 20, in which case no purchase order need be placed with the new supplier. Only when the sample evidence is strongly against it would the null hypothesis be rejected, in which case the purchase manager would place orders with the new supplier. The p-value of a test. We have understood earlier that a test of hypothesis is designed for a significance level, and at the end of the test, we conclude that we reject the null hypothesis at 1% significance level and so on. As discussed earlier, the significance level is somewhat arbitrarily fixed, and the mere fact that a hypothesis is rejected or cannot be rejected does not reveal the full strength of the sample evidence. An alternative and in some ways a better way of expressing the conclusion of a test is to state the p-value or the probability value of the test. The p-value of a test expresses the probability of observing sample statistic as extreme as the one observed if the null hypothesis is true. Hypothesis testing procedure. By now, it should be clear that there are basically two phases in testing of hypothesis. In the first phase, we design the test and set up the conditions under which we shall reject the null hypothesis. In the second phase, we use the test based on the sample evidence and draw our conclusion as to whether the null hypothesis can be rejected or else what is the p-value of the test. So the detailed steps involved are: Step 1. State the null and the alternate hypothesis. Step 2. Choose the test statistic, that is, the sample statistic that will define the critical region. Step 3. Specify a level of significance of alpha. Step 4. Define the critical region in terms of the test statistic. Step 5. Compare the observed value of the test statistic with the cutoff value or the critical value and decide to accept or reject the null hypothesis. Testing of population mean. Under different conditions, the test procedures have to be developed differently. We start by discussing the case when the population variance is known and the distribution of sample mean Z is known to have or can be approximated by a normal distribution. when population variance is known. We again refer to the purchase manager's decision problem. The purchase manager has to decide whether to buy castings from a new supplier who has claimed that his castings have higher hardness than those supplied by existing suppliers. The purchase manager knows that the mean hardness of castings supplied by existing suppliers is 20 and also that the standard deviation of hardness is 2.5. To test the claim of the new supplier, he picks up a sample of 100 castings from the new supplier and finds that the sample mean is 20.5. The purchase manager believes that the standard deviation of hardness of castings from the new supplier would not be very different from that of the existing suppliers. If the purchase manager decides to use a significance level of 5%, what should we conclude? We have understood earlier that unless and until the sample evidence is strong to the contrary, the purchase manager would not like to switch from the existing suppliers. The sample mean would be used to draw conclusions about the population mean, and so the test statistics is Z. We shall be in a position to reject H0 only if the sample evidence is strongly against it, that is, if the observed value of X is much larger than 20. The critical region will therefore be of the form X is less than equal to C, where C is a real number much larger than 20. The actual value of C would depend on this significance level used. The significance level is known to be alpha equals to 0.05. In other words, the probability of type 1 error should not exceed 0.05. We also know that the probability of type 1 error is highest when P is at the breakpoint value between H0 and H1, that is when mean is equal to 20. One-tailed and two-tailed test. In the previous section, we learned about a test where the critical region was found to lie under one tail, the right tail of the distribution of the test statistic. Such tests are called one-tailed tests in contrast with the two-tailed tests where the critical region lies under both the tails of the distribution of the test statistic. Let us assume that a purchase manager wants to test whether the mean hardness of castings supplied by one of the existing suppliers has changed from 20. If it has changed from 20, then he would like to take some corrective action. On the other hand, he would not like to initiate the corrective actions unless and until he is reasonably sure that the mean hardness has really changed. So he tests a sample of 49 castings from this supplier and finds that the mean hardness is 19.5. What should he conclude at a significance level, that is alpha of 0.05? Assume that A continues to be 2.5. In other words, until and unless there is an overwhelming evidence against it, he would like to believe that the mean hardness has not changed. The test statistic is again Z, but now he would reject H0 if mean is too far above 20 as well as if it is too far below 20. When population variance is unknown, we have so far been assuming that the population variance was known and so we could easily calculate the standard error of the mean. However, in many cases, that population variance is not known and we still want to draw conclusions about the population mean, then what should we do? Sample size is large. When the population standard deviation is not known, we have to estimate it from the sample, and as we have discussed in the previous unit, we use the sample standard deviation S to estimate the population standard deviation. Sample size is small. When the sample size is small, that is n is less than equal to 30 and the population standard deviation is unknown, the standard error of mean cannot be found directly. However, as we have learned in the previous unit, if the population distribution is normal, the sample standard deviation S can be used to calculate the value of a related random variable which has known distribution with the student's distribution with n-1 degrees of freedom. Therefore, if the sample standard deviation is known and this can always be calculated from the sample observations, then the critical region can again be defined in terms of the test statistic sample mean X. Testing of population proportion. We shall now discuss how tests concerning population proportions can be conducted. At this stage, we would request you to review the previous unit where we discussed the determination of confidence interval for the population proportion. In particular, recollect that the sampling distribution of the proportion is actually a binomial distribution which can be approximated by a normal distribution with the same mean and the same variance if n is sufficiently large so that both np and n into 1 minus p in the brackets are at least as large as 5. A personnel manager wants to know if the competence and the performance of its supervisory staff has changed. He knows from past surveys that 30% of the supervisory staff used to be rated in the super category. A sample of 50 supervisory staff have recently been rated and only 12 of them appear in the super category. What should the personnel manager conclude at a 5% significance level? In the absence of an overwhelming evidence against it, the personnel manager is likely to believe that the proportion of supervisory staff in the super category has not changed. It is not difficult to understand that even with proportions, one can use either a one-tailed test or a two-tailed test depending upon how the null and the alternative hypotheses have been set up. Testing for difference between means. Many a time the decision maker is interested in knowing whether two related populations are different from each other in respect of any parameter of the population. For example, a marketing manager may be interested in knowing whether the mean sales from a retail shop is affected by a display at the point of purchase. A personnel manager may like to know whether the job performance of a category of employees is affected by a particular training program. In these cases, the decision maker is not interested in concluding anything about the parameter value in either of the populations, but only whether the difference is significant or not. Dependent samples. We have so far discussed the case when the two samples picked up from the populations were independent. But we can also design our test in such a way that the samples are dependent. For example, if we want to know whether a training program helps in improving the job performance of a category of employees, we can evaluate the job performance of a sample of employees before they have undergone the training program. We can evaluate the performance of the employees again after they have undergone the training program. We would therefore have two performance evaluations for each employee in our sample, one before and the other after the training program, and so the two samples are dependent on each other. For each employee, the difference in the performance evaluations is caused by the training program and many other random factors which have a very insignificant effect on the job performance. Therefore, the difference in the performance evaluations can be treated as a random variable having a distribution of its own. In general, using dependent samples is better than using independent samples because the effect of all other major factors is eliminated and the difference can be attributed only to the treatment that we are studying. Such a design may not always be possible, but whenever we can design a test based on dependent samples, we are relatively more confident that we have isolated the effect of the treatment and that the two samples are identical but for this difference in treatment. Now let's summarize the unit. In this unit, we have learned how tests concerning statistical hypotheses can be designed and used. A statistical hypothesis is a statement about a population parameter or about a population distribution. As these tests are conducted on the basis of evidence thrown up by a sample, errors cannot be totally eliminated. All tests are designed to answer the question, is the sample evidence strong enough to reject the null hypothesis? The null and the alternative hypotheses are set up such that one of them and only one of them is always true. In the absence of a strong evidence to the contrary, the decision maker would be willing to accept the null hypothesis. Of the two errors that are possible in any testing of hypothesis, type 1 error, viz., the error in wrongly rejecting the null hypothesis is considered to be more serious than the other one and so is subjected to explicit control. All tests are performed at a significance level which defines the highest probability of type 1 error. All tests of hypotheses are conducted in two phases. In the first phase, a test is designed where we decide as to when can the null hypothesis be rejected, and in the second phase, the designed test is used to draw the conclusions. We also found that while testing population means, the test can be based on the normal distribution if the population variance was known or if the sample size was large. On the other hand, if the sample size was small, we had to design a test based on the t-distribution. Population proportions could also be tested on the basis of normal distribution. We then developed tests for testing the difference between two population means, both for independent and for dependent samples. When the samples were independent and the sample sizes were small, we developed a t-test based on the pooled estimate of the standard deviation of the two populations under the assumption that they were equal. Similarly, we also developed a procedure for testing the difference between two population proportions.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code MMPC 005, Quantitative Analysis for Managerial Applications. Course Coordinator, Professor Anurag Saxena, School of Management Studies IGNOU. Voiceover by Harpreet Kaur. Edited by Ashok Sharma. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.